Ore genesis. Ore is a natural occurring material from which a mineral or aggregate of value can be extracted for a profit. An ore deposit is an accumulation of a useful commodity that is present in high enough concentration and in sufficient quantity to be extracted at a profit. Syngeniki refer to the ore deposits that form at the same time as the host rock. These include deposits that form during the early stage of sediment diagenesis. Epigenetic refer to the ore deposits that form after their host rock. Hypogenes refer to the mineralization caused by ascending hydrothermal solution. Supergene refer to the mineralization caused by descending solution. Metallogeny, the study of the genesis of mineral deposit. Metallurgy, a geological, tectonic, lithological, geochemical feature that has played a role in concentration of one or more elements in the surface. Metallogenic epoch, a unit of geological time favorable for deposition of ores. Metallogenic province, a region characterized by a particular assemblage of mineral deposit types. Epithermal, hydrothermal ore deposits form at a shallow depth less than 150,000 meters at a fairly low temperature of 50 up to 200 centigrade. Mesothermal, hydrothermal ore deposits formed at intermediate depths. Hypothermal ore deposits form at substantial depth greater than meter 4,500 meters. An elevated temperature of 400 up to 600 centigrade. Economic geology is the study of the formation of extraction of element material that have some economic potential to serve society in financially. Key factors that contribute to the successful of exploration of a deposit, we have geological, economic, location and infrastructure, mining and processing technology, environmental and social, political and regulatory. Geological factor. This we commonly look at the grade of ore, size and volume of ore deposit, ore body shape and the continuity, mineralogy and metallurgy, which are very important. Economic factor. Commodity prices, cost of extraction, capital and operating costs, market demand. Location and infrastructure. Here we look proximity to infrastructure, access to water and power, remote and harsh environment. Mining and processing technology, mining method, ore processing and metallurgical recovery, waste and tailing management. Environmental and social factors, environmental impact, regulatory compliance, rehabilitation and sustainability. Political and regulatory factors. Here we have political stability, legal framework and taxes, permitting and licensing. Mineral resources and ore reserves. Mineral resources include the total concentration of mineral in a deposit, regardless of economic variability, classified in three categories: measured, indicated, and inferred. Measured mineral resources. These are mineral resources for which quantity, grade, or quality, densities, shape, and physical characteristics are so established that they can be estimated with a high degree of confidence. Measured resources can typically be converted into proven mineral reserve if they meet economic viability and other criteria. Indicated mineral resources. Mineral resources where quantity, grade, density, shape, and physical characteristics can be estimated with a reasonable level of confidence, though not precisely as measured resources. Indicated resources can often be converted into probable mineral reserve once further technical and economic assessment are completed. Inferred mineral resources. Mineral resources where quantity of grade and estimated on the basis of limited geological evidence and sampling. The confidence level is significantly lower compared to measured and indicated resources. Inferred resources cannot be used for mine planning and economic feasibility study until further exploration and more detailed data increase the confidence level. Ore reserve represents a portion of a mineral resource that can be reliable extracted, processed, and sold at a profit. It is classified as proven and probable reserves, which specify confidence level regarding the quantity and the quality of the mineral. All reserves must meet criteria for profitable extraction under existing market conditions, legal requirements, and with available technology. Classification of ores. Ores has been classified on basis on use of metal or mineral. First one, precious metal deposit. Here we have gold, which is ore. It is native gold, electrum, telluride, e.g. carbide, and crinolite. Uses jewelry, electronics due to high conductivity, density, investment. Silver. It is always native silver, argentite, astatite, chlorgyrite. It is uses jewelry, photography, electronics, medicine, antibacterial properties, and colors. Platinum group metals. Platinum, palladium, rhodium. It is all is sperite, grapelite, copperite. It is uses as catalyst in automotive, catalyst converters, electronics, jewelries, and fuel cells. Classification of ore based on the use of metal or mineral. We have the second one is base metal deposit, which we have copper, lead, zinc, and nickel. We have precious metal deposits, which we have iron, we have manganese, chromium. We have the light metals deposits, aluminum, titanium, magnesium. We have high technology metals, rare earth element, cobalt, tin, tungsten, molybdenum. We have energy metal deposit, uranium, thorium, lithium. Classification on the basis of types of mineral. We have native ore, we have sulfide minerals, we have oxide minerals, carbonate minerals, halide minerals, silicate minerals, phosphate minerals, sulfate minerals. Classification of ore deposit has been classified into Ringgreen classification, which was based on thermal, epithermal, mesothermal, hypothermal, which was based on the basis of temperature. Classification of ore deposits based on tectonic settling. We have deposit at oceanic ridge, divergent plate margin, which we have volcanogenic massive sulfide deposit, exhalative deposit, manganese nodules. We have chromium, PGE, as it stores with mafic rocks. Deposit at convergent plate margin, polyferro, copper, molybdenum deposit, as a base metal deposit like copper, lead, zinc, molybdenum. Precious metals, lead, zinc, and silver. Depositing in Craton Rift system. Deposit of fluorite, barite in granite evaporate in rift basins. Carbonatites contain rare earth element, diamond, and kimberlites. Deposit in an intercontinental setting. We have nickel in the PGE in layer intrusion, titanium in anothites, iron oxide in the copper, and silver. Yes, lead, zinc, sedimentary copper deposit, diamond, and kimberlite. Classification based on ore forming process. Here we are looking about magmatic ore deposit, ore that forming by accumulation of mineral that crystallize direct from the magma, which we have ore deposit in mafic and ultramafic rocks, which we found chromite, copper, nickel, iron, sulfide, nickel, copper, iron, diamond, and kimberlite. Ore deposits associated with ferric intrusion. We have copper ore, rare earth element. Also, we have hydrosemal ore deposits. We have polyferro deposit, epithermal deposit, volcanogenic massive sulfide deposit. We have sediment hosted stratiform deposit, Mississippi Valley type deposit. We have skarn deposit, carbonate hosted lead zinc deposit, iron oxide copper gold deposit, and we have sedimentary ore deposit, which comprises banded iron formation, BIFS, pressure deposit, evaporate deposit. We have sedimentary exhalative sidex deposit, phosphate deposit, laterite deposit, manganese nodules deposit, supergene ore enrichment. Also, we have magmatic ore deposit, which is normally found after cooling of the magma, and it is comprises in basaltic and acidic and rhyolitic magma, which it comprises some process which like fractional crystallization and ore forming processes, which is a critical ore forming process that significantly contributes to the concentration of various metals and the formation of economically important ore deposit. Processes in a fractional crystallization, magma cooling. When magma rises forward the earth, it begins to cool. As it cools, certain mineral crystallize at specific temperature. The crystallization sequence is largely governed by Bowen-Langston series, which describe the order in which mineral crystallizes from a cooling magma. Crystallization and settling. Air-formed mineral, e.g. olivine, pyroxene, are generally denser than the surrounding liquid magma and will settle to the bottom of the magma chamber. This process is known as density stratification. As this mineral crystallizes and are removed from the melt, the remaining magma become increasingly rich in elements that are not easily incorporated into the crystal lattice of the early forming mineral known as incompatible element. As magma becomes to cool, compatible elements prefer to enter and stay within the crystalline minerals rather than remaining in the molten phase. They bond with minerals that form at high temperature like olivine and pyroxene. Compatible elements. Compatible elements are those elements that rarely incorporate in the crystal structure of mineral during magma crystallization. Influence on ore formation. These compatible elements are removed from the material. They are generally not concentrated in the residual liquid phase, which reduce their potential for forming ore deposit. Incompatible elements, on the other hand, do not easily fit into the crystal structure of the earth-forming minerals. For instance, include potassium, barium, uranium, thorium. Influence on ore formation. These incompatible elements remain in the metal until the final stage of the magma evolution. They become highly concentrated in the residual liquid. This concentration can lead to the formation of ore deposit of the element are then transported in hydrothermal fluid or deposited in ore forming environment. Chromite deposits in larger layered intrusion in Bushveld in South Africa. Neil Irvin, in two papers published in 1997, Irvin published that under a normal condition, 1 up to 2% chromite crystallizes together with olivine. Mafic ultramafic liquid such as the parental magma of the Bushveld complex brought in the feed of the olivine, such as the liquid initially crystallized olivine, was removed to drive the residual liquid composition to the cocktail, at which point chromite started to crystallize. Partial melting as an ore forming process. Partial melting is in complete melting of the rock, resulting in the production of magma that is chemically different from the original rock. Mechanism. When rock are subjected to high temperature and pressure, certain minerals within the rock have lower melting point than others. As a result, these minerals can melt while others remain solid. Mechanism of enrichment. As the partial melting occurs, the remaining solid residue become depleted in this incompatible element, while the resulting magma become enriched in them. This concentration of economically valuable metals occur because the melt can transport this element more effectively than the solid rock can. Example of ore deposits formed by partial melting is tin, tungsten, molybdenum, uranium, lithium, beryllium, titanium, niobium, and rare earth element. Liquid immiscibility is an important ore forming process that occurs when two immiscible non-mixing liquid phases separate from each other within a cool magma. This separation allows certain metal to become highly concentrated within one of the liquid phases, leading to the formation of economic variable ore deposits, which include silicate melt, sulfide melt. Liquid immiscibility in ore forming process factor that promotes sulfide immiscibility. There is high sulfur content. There is low oxygen fugacity, assimilation of sulfur-rich country rock, decompression and magma mixing, presence of volatile. How other factors control the metal turnover? Chalcopyrite elements like nickel, copper, PGE have strong affinity for sulfur liquid relative to silicate metal. When sulfide liquid form, this metal passion preferential interfere from the silicate magma.